Internal flows. Hello, everybody. Welcome back. And we're going to continue discussing internal flows, which we started on Friday. So let's see. Um, okay. So internal flows are the flows that happen inside pipes or between parallel plates or in between uh, two surfaces. And the key here is that these two opposing surface prevents an indefinite growth of the boundary layer. So when we discussed boundary layers and external flows, which is the topic of this evening's quiz, we saw that the boundary layer increases as we go farther downstream. And why does it increase? Okay, because we have momentum transfer that slows down the fluid of thicker and thicker regions from the point of view of fluid flow. And also, we saw that we have heat transfer as the fluid is going downstream. The heat is penetrating deeper and deeper into the fluid. In a laminar boundary layer, we saw that the thickness increases with the square root of the length, right? It's a parabolic growth. For the case of internal flows, things are very much the same, except that this growth of the boundary layer cannot go on indefinitely because we have the other opposing surface. So in this schematic we see here, we see how the fluid is getting into a tube and a boundary layer starts to form on one side of the tube, and the opposing side of the tube, we see how the boundary layer also starts to form and gets to a point when these two boundary layers collide. This region in which the boundary layers are developing is what we call the entry region. And when the two boundary layers have collided, we call this the fully developed region. Because we have two different types of boundary layers, we have the viscous boundary layer, and because we have the thermal boundary layer, we're going to have two entry regions. We're going to have a hydrodynamic entry region, and we're going to have a thermal entry region. In addition, depending on the nature of the flow, we have seen that the boundary layers can have different behavior, and that is going to affect our entry regions too. So if we have a laminar flow, we're going to have an expression and a different expression for for length of entry region for the case of turbulent flows. What we did see on Friday is that that we can define in a inside a pipe in internal flows, right? We define a mean velocity, right? It's different than in the case of external flows, in which we would define a u infinity that was the velocity far away from the plate, the velocity just outside the viscous boundary layer, right? Now we talk about a mean velocity that relates to the volumetric flow. We also mentioned that the criterion for turbulence is different than the criterion for turbulence we had on a flat plate. On a flat plate, we said turbulence is triggered when we reach a critical Reynolds number based on the length of the boundary layer. And that critical boundary Reynolds number was 5 times 10 to the 5. In the case of flow inside a tube, for the case of a circular tube, what we determine the Reynolds number based on the diameter of the tube, not the length downstream in the tube. It's the diameter. And the critical Reynolds number based on the diameter, right? Reynolds D for turbulence is 2300. it's a very different number than the other, but the number in itself for this transition to turbulent is not, doesn't have a particular meaning. It's just when it happens. By the way, these numbers are not God-given because they are affected by things such as roughness, right? That of which we are not discussing in this class. So this is a great start because these are real life equations. But if we ever need to design something that goes deeper, we need to know that these criteria for turbulence requires a little bit of deeper thinking than what we are doing here. So the book gives a formula for hydrodynamic entry length without any explanation, but we could see that using this concept that the entry region is the region in which the two boundary layers are developing, we can calculate how long it takes for the boundary layer thickness to reach half a diameter, right? To reach a value of a radius. And although this is a very rough approximation, we end up with a prediction that the entry length of inside the hydrodynamic entry length, we use the solution from Blasius, and we obtain something like 0.055 Reynolds D. So that the entry length is 5% of Reynolds based on the diameter for laminar flows. And the exact number given in the book is 0.05. We were saying 0.055. Using the formulas we had, we derive it without solving any differential equation. And that's the key. If we have to, we will solve them, and we will even love them. But if we don't have to, we don't. And in this case, we didn't need to solve any differential equation, and we can anticipate the entry length for laminar flow. If the flow is turbulent, this, we don't have a better way of dealing with it, but the book suggests that the entry length is for turbulent flow is of the order of 10 diameters, right? 10 diameters could be a little bit longer, but those are subtleties. We're gonna call it 10 in this class. Thermally, and this is where we stopped on Friday, thermally, we also have an entry length. Now, in the case of fluids with Prandtl bigger than 1, such as water that has a Prandtl of 7, or oil that has a Prandtl of 10,000, right? The viscous boundary layer is significantly larger. It's significantly larger. So this entry region in the fluid entry is very short compared with the thermal entry. Let's see if I have a better schematic. No, I'm gonna make one. So let's put technology to good use here. So let's say we have a pipe. And let's say we have flow coming in. So I'm gonna make in blue the entry, the hydrodynamic entry. So we would have a boundary layer that grows something like this. Something prettier than that, actually, I would hope. Right, these are the two boundary layers developing. And this is what in the notation of the book, that is very awkward, but I decided to stick to it. They call it X fully developed, comma, hydrodynamic. Now, we know that for the case of things like oil, the thermal boundary layer is a lot thinner. So the thermal boundary layer would be something like this. And this length is going to be the thermal entry length, X, fully developed thermal, right? This part here, in which both boundary layers are happening, is when they call it the combined entry. Question to you: if Prandtl equals 1, is the thermal boundary layer, is the thermal entry length longer, shorter, or the same as the hydrodynamic entry length? I would like to see this in the chat. I would love to hear somebody have a thought. Prandtl equals 1, similar to the case of air. Is the same? Of course, the same. Thank you so much. Because we have, when Prandtl is 1, we have the Reynolds analogy that says that the solution for fluid flow is the same as the solution for heat transfer. So both boundary layers are going to be the same, both entry lengths are going to be the same, and that's the case of combined entry. And we're going to touch on that soon. So if we want to analyze in our notes the thermal entry length, we would do the same as we did for the hydrodynamic entry length. Here we have the thickness of the thermal boundary layer, and we have a 3 here because this is a case we're talking about Prandtl's more or less like 1 or bigger, and we needed to use Blasey's solution. So here we go, and we say the thickness should be half diameter, and for the characteristic velocity, we're going to use the maximum velocity, same as we did before for the case of the hydrodynamic boundary layer. And what do we get? We solve this for entry length, and we get this expression that says 0.055 Reynolds times Prandtl. And what is the exact solution from the book is 0.05 Reynolds times Prandtl. Give or take, it's not such a big deal. If I ask you to use the exact solution or the exact or the most accurate solution, this one is the one to use, but the only difference is 10%. And but the functional dependence is exactly the same, right? And now we, instead of having just a formula that came out of nowhere, we have power to work on it. We understand where it comes from, right? We know what makes it tick. And that's the most important thing. Plug and chug, you don't need me. You have proven that you're good at that. You're in 3rd year, maybe more, right? Now, understanding what's going on, that's the joy of engineering, and is what can unlock us to help us invent things that don't exist today. And that's our one hope in Canada. If things are easy, chances are somebody else is going to do it and steal them from us. But if we can do the tough things, we can be creative and invent new things, then we're good. All right. For the case of entry flow, we have that the entry length, the thermal entry length, is also 10 diameters. And of course, it makes sense because if you remember when we discussed turbulent boundary layers, we said that the turbulence caused local advection. And eventually, if the turbulence is high enough, that advection is dominant over the diffusivity, the thermal diffusivity or the kinematic viscosity, such that both the effective thermal diffusivity or the effective thermal kinematic viscosity would be the same because they were determined by turbulence. So in turbulence, the effective Prandtl number is 1, right? Like kind of a Reynolds analogy. and both boundary layers have the same thickness, therefore they would have the same entry length. And that's exactly what the book says. All right, so now that we have discussed entry length for both hydrodynamics and heat transfer, let's see a little bit what happens with the heat that is transferred from the tube to the fluid. This is another difference with external flows. In external flows, I can put all the heat I want from my plate. And because the external flow is assumed to be infinite, then all that heat goes away, but does not affect the temperature of the fluid far from the plate. Right? The heat penetrates into the fluid, but it doesn't change. Eventually, I can always go far enough to a point in which there is no effect from the plate on the fluid. That's not the case of tubes, because in a tube, eventually, I know the tube is going to have the fluid is going to have the same temperature as the tube. If the tube is long enough, that's going to happen, right? That's a big difference with external flows. So we have two differences. Internal flows have an entry length that does not exist on external flows, and internal flows also affect the overall temperature of the fluid, while in external flows, far enough from the plate, the external temperature does not change. So let's start by defining the convection coefficient in internal flows. And here we have this equation, that is equation 827 in the book. And this equation looks innocent, and to some extent is innocent, but has a twist. And this is a twist. We have heat flux just through the surface, just as we have done all the time for convection, equals H times delta T. And delta T is Ts minus something. But here's the catch. In external flows, H was defined based on the temperature difference between the surface and the free flow, T infinity. Surface and free flow. Here, we don't have a free flow. So what they use is temperature, the surface temperature minus average temperature. It's a subtlety. The formula looks so much the same, but this is not a maximum temperature, not maximum, not free flow, because there's no such free flow either. This is the mean, the average temperature. And the average temperature is what we have been using all the time without explaining it all too much when we talked about advection in pipes. We would calculate heat fluxes based on temperature differences without ever saying that the temperature actually had gradients. In reality, those were average temperatures, mean temperatures. That is what is indicated here. Important to keep in mind. So, something interesting, that this is a figure down here related to what we were discussing before about the entry length. So we know from our experience with flat plates and external flows that at the leading edge, the boundary layer is thin. Therefore, there is a thin layer of insulation and a high rate of heat transfer, the same way that a thin jacket gives you a lot of heat transfer to the cold, which you don't want, right? And as we go down in a flat plate downstream, this boundary layer is thicker and thicker and thicker, and the convection coefficient is lower and lower and lower. In internal flows, once we have a fully developed flow, the boundary layer stops growing. And because it stops growing, then we reach a plateau and we reach a constant value of heat transfer coefficient. And this is what we see in this schematic here that maybe doesn't show so good. So let's try to make a schematic in So this would be distance x inside the pipe, right? The pipe is here. Oop. Let's get a cross section of the pipe, and the fluid is coming in. And x equals 0 is the entrance of the pipe. And this vertical axis is convection coefficient. And what do we have? Well, our equations say that the convection coefficient at the leading edge is infinite, but we know it's not infinite. It's just that as if we assume there is flow heat transfer only in the direction transverse to the flow, right? Then would be infinite. But we know that right at the leading edge, the heat transfer is not 1D heat transfer, is actually 2D. So it's infinite, comes down, comes down, comes down. In the case of in the case of a flat plate, we saw that this would come down asymptotic to 0. But in the case of a pipe, we have a value at which it actually, the two boundary layers collide, they stop increasing in size, and then we get a constant value. And this is called the heat transfer convection coefficient for fully developed flow. And this value where the convection coefficient becomes asymptotic with the fully developed flow, this is our entry length, thermal entry length, X fully developed thermal. So in the entry length, we have high heat transfer because the boundary layer is so thin. In the fully developed flow is when we have kind of low heat transfer, right? It's not too low, but it's just the temperature profile is established. It's more or less shallow. It's not sharp anymore as like the beginning of a boundary layer, and that stays for the length of the tube. So so let's do this energy balance in a tube, right? And discuss, put together concepts we have seen before. So so the energy balance in a tube, and we have this balance here, which we have done many times already. I'm not going to get into details, right? But we have Q in minus Q out plus Q generated, and let's forget about Q generated. Let's talk about steady state, right? And let's say, like in the case of all heat exchangers, the Peclet number is much bigger than 1. Therefore, we can neglect conduction in the direction of the flow. And we end up with this equation that is Q advection in minus Q advection out, right, is what was mass times the change in enthalpy. And we did this in the week, what week was that? We did this on week 4 of differential control volumes, and you came up with this expression that says temperature gradient is the perimeter of the pipe, heat flux on the surface, times the mass flow and the specific heat of the fluid. In this case, we're assuming no phase changes. This, we did it in, and perhaps with slightly different notation, but this concept, exactly as we did it here, we did it in week 4 of class. Now, this equation here is actually very useful to us, and it's very general. It says the gradient depends on the heat flux and the mass flow. So let's see first the case in which the pipe is receiving a constant flux of heat. This can be the case, for example, when we have a condenser in which liquid flows inside the tube and there is condensation happening on the surface of the tube. In condensation, right, we would be depositing, an amount of the latent heat, so energy would be coming in. So in this case, right, we have in this graph, X is the direction into the pipe, right, the direction downstream. This vertical axis is the mean temperature of the fluid, right? And we can solve this equation that we have here. If surface heat flux, right, Q double prime, is constant, right? So all these other terms are constant. Therefore, the derivative is a constant. That means the curve will be a straight line. And here we would have the straight line that says the fluid comes in at Ti, at the inlet temperature, and the fluid keeps increasing its temperature as it goes downstream. Right? That's what this general equation that comes from week 4 of class tells us in this case. What else do we see from working with this equation? Well, in this equation, we had the mass flow and specific heat. And we see that if we increase the mass flow, right, the slope is going to be shallower. And of course, we know this. Anybody who has played with a heat exchanger knows this. If I'm putting some amount of heat and I flow water through a tube, the water is going to warm up. If the water is flowing very fast, it's going to get less heat, right? It's going to have less increase of temperature, right? Less heat per unit mass. And this is what comes out straight from this equation. Also, what this equation says is that if I increase the flux of heat into the pipe, of course, I'm going to increase temperature faster. So this is pretty good and relatively easy to make sense, right? But let's think a little bit deeper about this heat transfer inside a tube. So using this equation of week 4 of class, we could establish this equation for the case in which heat flux is constant. We end up with this other equation that is not a differential equation anymore. It's just an algebraic equation saying that temperature increases linearly. Now, let's think, and sorry, I said temperature, but I meant mean temperature. Now, what is the surface temperature of the pipe going to be? And here it gets really interesting. Because we know that the mean temperature is going to increase linearly. But if we look at the expression for convection, we have that heat flux is convection coefficient times surface temperature minus the mean temperature of the fluid. Let's assume we're heating up the fluid, right? Therefore, we can solve for surface temperature, and it's going to tell us that the surface temperature is going to be a little bit hotter than the mean temperature. Of course, the pipe has to be hotter than the fluid if we want heat to go into the pipe. How much hotter? Exactly, we can do it because we solved this equation based on the heat transfer mechanism of convection that we saw on the second week of class, right? This class is always the same, just making one more twist on the things we learned in the first few weeks of classes. But here is where the fun comes, because this equation doesn't seem to say much, except that the heat transfer coefficient H in the entry length is high, and in the fully developed flow is constant. So what do we know? That the surface temperature of the pipe in a fully developed flow is going to be something constant that doesn't change with the length of the pipe. However, during the thermal entry length, H can be very high at the beginning, and it lowers down to the steady state value. High enough to be, let's call it infinite, H. So in the entry length, this term here, the heat flux divided convection coefficient, this term here is very small. It starts at 0 pretty much, right? And eventually opens up to be, increases to be the steady state value. Therefore, if we want to look at the surface temperature of the pipe from the entrance of the inlet of the tube all the way downstream, what we would see is that the mean temperature increases linearly. However, the surface temperature starts being very low, well, very low. The temperature difference between the surface, the pipe and the fluid starts being the difference negligible, and that difference increases until it reaches a steady state value of difference in the fully developed flow. Super interesting. The entry length of a pipe is actually very important. It has very different properties than the fully developed flow. And the entry length has higher heat transfer coefficient. If we're designing heat exchangers, not reaching fully developed flow is a good thing, right? You don't want fully developed flow because you have, in the entry length, you have a higher heat transfer coefficient. So very interesting to see that the surface, that the pipe and the fluid have like a varying temperature difference between them. I think that's pretty interesting. Okay. What happens if instead we say that the surface temperature is constant? The pipe has a constant surface temperature. And let's see. Okay. So let's see when the surface temperature is constant. We go back to the equation that comes from week 4 of differential control volumes. Right? So that was a painful week 4 of differential control volumes. But you see, we put it all there, and we can go and reassess it if we need it. But everything we're discussing now comes from what we did then. We're not doing anything new. So we have this equation, and if we say temperature, the pipe temperature is constant, right? We would have Q convection, right? Q convection is H times surface pipe temperature minus average mean temperature of the fluid, right? And look at this. Now we got a first order differential equation, right? We have this differential here, the derivative of mean temperature with distance, and here we have the mean temperature. So solving it the same way we have done in the differential control volumes unit, or if you look at the math refresher that is uploaded, the solution to this first order ordinary differential equation is an exponential. And here is the exponential that we have gotten many other times before. And in this exponential, guess what? We are going to have a characteristic length too. A characteristic length for during which the fluid is going to transition from its initial temperature, the inlet temperature, until it adopts the temperature of the pipe. This characteristic length is not the entry length. Entry length is related to boundary layers. That's what it is. This concept here has nothing to do with boundary layers. This concept here says that once the fluid is, say, fully developed and there is no boundary layer anymore, still the fluid keeps increasing in temperature. And even if it is not fully developed, depends on age, right? The fluid temperature is increasing in average, aiming to reach the same temperature of the pipe. So we have here this graph where we see the curve that is so similar to the curves we have seen in many times before, for example, in lumped capacitance or in lumped capacitance for sure, but also we saw it when we were talking about advection heat transfer. So X equals 0 is the inlet of the pipe. We move downstream and we started inlet temperature. The pipe has a surface, a temperature Ts, temperature of the surface, which we said is constant. And we see that the temperature increases and eventually becomes asymptotic with the temperature of the pipe. Question to you. If we're in this region, right, at which the temperature of the pipe, the fluid, it matches the temperature of the pipe, do we have high or low heat transfer at this part here? Anybody wants to venture a guess? High or low heat transfer? When the mean temperature of the fluid reaches the temperature of the pipe. Okay, so if the mean temperature of the fluid is the same temperature of the pipe, we have thermal equilibrium, right? When two things are at the same temperature, there is no heat exchange. So all this pipe here, all this part here is wasted pipe. If this was a heat exchanger, all this part here, we paid for pipes, we paid for heat exchanger we're not using. The heat transfer happens between the temperature of the fluid and the temperature of the pipe. So here the heat transfer is high. As the fluid is heating up, the heat transfer is being reduced. And by the time we are around at this characteristic length, right, for thermal equilibrium into the pipe, which has nothing to do with boundary layers, therefore has nothing to do with entry length, this other length is more or less the length you want in a pipe. If you go longer than that, your heat transfer is so little, but the price you pay for the pipe is the same price you pay for the pipe here that is transferring a lot. You're way better off having two short pipes than one long pipe. Now, having two short pipes sometimes means things are more expensive. You need to weld both ends, right? While one longer pipe can be cheaper. So there is a balance. For sure, you don't want to make it too long because you start losing money again. You see that the surface temperature, the pipe temperature, right, is the hot surface, and the fluid have a difference. And here we have high heat transfer. And as the fluid progresses, the temperature difference is changing. So how do we assign an amount of heat transfer by convection when the temperature is changing? That's not trivial. We want to say H delta T. but delta T is changing. So people thought about this, and for the case in which you can say the H is constant, you have you have an exponential variation in the temperature of the fluid. When you have an exponential variation in temperature of the fluid, you can do a little bit of math, which is in the book, but we're not doing, we're fine. And it tells you that you can say heat transfer is H delta T. When delta T, which is changing, you use the delta T log mean, which you might have already seen in some other classes. And the delta T log mean comes from doing the integral of heat transfer as the temperature of the fluid is changing. And this would also apply in a heat exchanger when the temperature of both fluids are changing. So delta T log mean so far for internal flows is defined this way, right? That comes from the math, and is delta T at the outlet, delta TO is at the outlet, minus delta TI, that is delta T at the inlet, right? So to give you an idea, delta T at the inlet in this example we have in this curve would be TS minus TI. Let's say that the outlet is here at XC. So the delta T at the outlet would be TS, we said is constant surface temperature for the pipe, minus this other one here. You see, this one is relatively small. This one is relatively large. So we do the difference, of course. In this case, it's going to give us negative, but I'm not going to worry about that. This part is going to give us negative. And then divide by the log of the ratio of these two. And this because delta T outlet is smaller than the delta T inlet, this log is going to be negative 2. So negative over negative is positive, and the delta T log min is always positive. You can flip O and I, you're going to get exactly the same result. So this comes from the math doing the integral of heat transfer when the temperature of the fluid is varying. Using this concept of delta T log mean, I can say that the heat that was transferred by convection is the average heat transfer coefficient times the surface area. In this case, the surface area is the surface of the pipe, right? Pipe times diameter times length, the surface of the pipe, times the delta T log mean. And the delta T log mean is like some magical delta T that makes our equation look like the same as before, as we have always used, but now accounting for something that didn't happen before. That is the fact that the temperature difference is varying. So this is a really, really smart thing that is used very much for heat exchangers. And it all has its roots in these internal flows. We didn't need to define delta T log mean before, because a fluid in external flows doesn't change temperature. Now in internal flows, the fluid changes the mean temperature, and we have a very easy way of calculating it. You do not need to memorize this. It's in the formula sheet I already uploaded, or it's in the book, right? It's such a smart thing. So we have 5 minutes. Let's do an example with numbers. Yay. So let's calculate. Let's say we have a condenser, and that is condensing steam on the surface of a circular tube of inner diameter 50 millimeters, right? So this is the diameter through which the fluid is going. Let's say it has a length of 6 meters and maintains a uniform surface temperature of 100 degrees. So I said something wrong before. I used a condenser as an example of constant heat flux. That's wrong. A condenser is not a constant heat flux system. It's a constant surface temperature system. Sorry about that. I stand corrected. And this example has it properly. So the surface of the tube is at 100 degrees C. And you can ask me, is it the inner surface or the outer surface? And if you remember, we said that in heat exchangers, we want the thermal resistance of the pipe to be so small that there is essentially no temperature difference between inside and outside the walls of a tube. So doesn't really matter, but this is the inner surface temperature that is very close to the outer surface temperature of the pipe, because the thermal resistance of the pipe itself should be so small. So water is flowing inside the tube at a rate of a quarter kilograms per second, and the inlet and temperature is 15 degrees, and the outlet temperature is at 60 degrees. So water is coming in into the tube at 15 degrees, coming out at 60 degrees, right? And is the receiving heat from condensing at 100 degrees on the surface of the tube. The tube is always at 100 degrees. Here, we calculated the specific heat of water using the book. So typically when you have temperature dependent properties, what are you gonna do? You have to pick one, because all these formulas are for a single heat capacity. So how about if we pick the heat capacity, the specific heat at the average temperature between the inlet and the outlet? That's what the book suggests. And it's a reasonable approximation. So you get the temperature halfway between inlet and outlet, and at that average temperature, you take the specific heat, which is this one that we have here. Let's calculate the average convection coefficient in this case. We know the flow of the water, we know the temperature difference in the water. So if we know how much water is going and how much it changed temperature, I have a sense of how much heat it absorbed. We're going to put it in formulas in a second, right? And I also would know the temperature difference, so I can calculate it. So step number one, I would do my energy balance equation, which is the same we have done for differential control volumes. And we have that the heat of advection is mass times specific heat times delta T. This we have done a million times before. And actually, for the future, I'll clean out the notes, because all this analysis we have already done in differential control volumes. This amount of heat that the water absorbed came from the steam, and it comes from the surface of the tube, from the inner surface of the tube into the fluid by convection. And how do I calculate the convection into the tube? Is H, this is H, the convection coefficient for internal convection times delta T log mean, which we just discussed, times the area of the pipe. And we have this balance here. From this balance, we can solve for the convection coefficient. That is mass flow times specific heat times temperature difference. For the advection, we don't need to do log mean for the advection. For the advection, the water comes at one temperature, goes out at another temperature. And advection, no problem with that. Advection, we were good. So we have this temperature difference for advection. And for convection, heat transfer between the fluid and the pipe, then we have to do the delta T log mean. Then it is just a matter of plugging and chugging, and we end up with a result. So what we are learning little by little is the subtleties of how to calculate a heat exchanger, understanding things from the very basics. Let's stop here, and I'll be back at 2 for office hours, and after that, I'll see everybody for the quiz at 5. Thank you very much. Let's stop here.